Imagine standing at the edge of a vast, uncharted ocean that stretches not just across space, but across the very fabric of reality itself. Now, picture yourself peering through the most powerful tools humanity has ever built. Not to explore distant galaxies, but to glimpse the tiniest building blocks of existence. This isn't science fiction, it's the incredible journey we've taken into the unseen world around us. Every microscope, every particle collider, every groundbreaking discovery has been a step deeper into that ocean, revealing layers of reality we never knew existed. But here's the astonishing truth. The deeper we go, the more we uncover something remarkable. The act of trying to see the smallest things doesn't just reveal their shape, it changes the very nature of space and time. As we push the boundaries of our tools, we don't just find new answers, we find the edges of what we understand. And that's where the magic happens. Today, we're going to pull back the curtain on how we see the unseen. We'll follow the trail of light, electrons, and energy as they become our eyes into the atomic world. We'll discover why some things remain invisible to our eyes, and how we hacked the rules of physics to make the invisible visible. Along the way, we'll meet the scientists who dared to ask, what if we look closer and found that the universe doesn't just reveal its secrets, it rewrites them? So, let's begin with a simple question. How do we see anything at all? It turns out, the answer isn't as straightforward as you might think. To see the world, we need more than just ice, we need light, matter, and a little bit of quantum curiosity. And when we put those pieces together, we unlock a universe far stranger than the one we can touch. Imagine standing at the edge of something extraordinary, an invisible frontier, where curiosity isn't just a habit, but a superpower. The universe has already handed you the keys to unlock its deepest secrets. And the journey begins with a simple question. What happens when we push the limits of what we can see? You don't need to accept the boundaries others have drawn. You don't need to wait for permission. The tools exist right now, and the path forward is yours to explore. Think for a moment about how we've uncovered the unseen before. Light bends, waves ripple, and particle 7, solid, tangible particles can behave like invisible currents of energy. The moment you start asking why and how, you're no longer just observing the world, you're reshaping how you understand it. That's the magic of active learning, the kind where you don't just memorize equations, but where you feel them. Where you ask, what if I could see this? And then you build the experiment to find out. This isn't passive knowledge. This is discovery. This is the thrill of realizing that the universe responds to your questions. Now, let's zoom in. Not with a microscope, but with something far more powerful, the very energy of light and matter itself. Light is made of particles called photons, each carrying a precise wavelength, a precise energy. And here's the revelation: the smaller the thing you want to examine, the higher the energy you need to illuminate it. A photon's wavelength determines how fine the detail you can resolve. Need to see something a billionth of a meter wide? You'll need photons with a wavelength that small. And that means energy packed tighter than you might imagine. It's like shining a flashlight into the dark, but instead of light, you're using waves of pure energy to carve out the shape of the unseen. But light isn't the only player. Electrons, those tiny, darting particles we often think of as solid, can also act like waves. And just like photons, their wavelength dictates how small the features they can reveal. Push an electron faster, and its wavelength shrinks. Increase its energy, and suddenly, it's not just a particle anymore. It's a probe, a tool capable of uncovering dimensions hidden from slower, less energetic electrons. What's even more fascinating? When electrons move fast enough, their behavior starts to mirror that of light. Their energy scales the same way. Their wavelengths compress to the same precision. The distinction between light and matter begins to blur, and what remains is a single, unifying rule. The higher the energy, the smaller the scale you can explore. So here's the question burning in your mind. Can we keep going? Can we shrink our focus until we're staring at the heart of an atom? Can we peer inside a proton and see the quarks dancing within? And if we could, what would it take? Let's say you want to resolve something as tiny as a proton just 10-15 meters across. Plug that into your mental equation, and you'll find the energy needed is staggering, about 1 billion times more powerful than visible light. That's not just theory. That's what scientists did in the 1960s at places like the Stanford Linear Accelerator Center. They fired electrons at protons with energies reaching 20 billion electron volts and watched as the electrons scattered from point-like objects in pseudo-objects we now call quarks. For the first time, they saw that protons weren't solid blobs, but complex, structured worlds. And that discovery, it earned them a Nobel Prize. But let's go deeper, much deeper. Imagine shrinking your focus to a scale 100 million times smaller than an atom, something on the order of 10-18 meters. How much energy would that take? 1 trillion electron volts, a teraelectron volt, and guess what? Humans built a machine to reach those energies. The Large Hadron Collider isn't just a tool. It's the most powerful microscope ever created. It hurls protons at nearly the speed of light, colliding them with forces that rip apart the very fabric of the Higgs field, briefly creating particles so massive they shouldn't exist, particles that vanish almost instantly, leaving behind clues to the universe's deepest workings. It's as if you're shining a light so bright it can carve through the air itself. Yet even this is just the beginning. Can we push further? Can we keep zooming in until we hit the absolute smallest thing possible? Here's where the universe hits back. The deeper you try to look, the more the rules of physics resist you. Energy isn't just a tool, it's a force that bends space-time itself. Focus too much of it in one place, and you don't just see smaller. You warp the very stage on which the observation takes place. The more energy you cram into a tiny space, the more gravity responds. Space-time isn't a rigid backdrop, it's a living, breathing fabric that stretches and sags under the weight of extreme energy. At some point, the energy becomes so concentrated that it collapses inward, forming a black hole region where the pull of gravity is so strong that not even light can escape. Suddenly, your attempt to see finer detail doesn't reveal the unseen. It hides it behind an event horizon. So when does this happen? Einstein's equations give us the answer. There's a critical Schwarzschild radius where any object becomes a black hole if you squeeze it small enough for a given mass. If you shrink it past this point, gravity wins, and since energy and mass are interchangeable thanks Einstein, we can rewrite this rule in terms of energy. The more energy you pack into a space, the smaller that space can be before it collapses. There comes a moment when adding more energy doesn't sharpen your view. It erases it. That moment defines the Planck length, a scale so small it's almost unfathomable. Around 1035 meters. It's the point where quantum mechanics, relativity, and gravity collide in an irresistible embrace. Try to probe smaller than that, and you don't just fail to see. You create a black hole instead. The universe has a built-in limit to how finely you can look. And it's not because we lack the technology. It's because the laws of nature themselves refuse to let you peek any further. So what does that energy look like? The Planck energy is a number so vast it makes the Large Hadron Collider's efforts seem like child's play. We're talking 1019 giga-electron volts an energy so immense that if you tried to build a machine to reach it, you'd need a particle accelerator ring larger than our solar system. It's a reminder that the universe has its own boundaries, its own way of saying, this far and no further. But here's the beautiful part. You don't need to accept these limits as insurmountable. They're not walls. They're invitations. The Planck length isn't the end of the road, it's the horizon calling you to explore what lies beyond your current understanding. Every time we thought we'd reached the smallest thing possible, from atoms to quarks to the Planck scale, we've only scratched the surface. The tools we have today are primitive compared to what we'll create tomorrow. The questions we ask now are just the first whispers of what we'll demand to know in the future. So what's next? The answer lies in your hands. The same curiosity that drove you to ask, "How small can we go?" is the same force that will lead you to ask, "What's beyond?" The universe doesn't just reveal itself to those who wait. It unfolds for those who dare to push. And the most remarkable thing, you don't need to be a scientist in a lab coat to be part of this journey. You just need to refuse to stop asking, to keep experimenting, to keep reasoning, to keep discovering for yourself. Because here's the truth. The universe is designed to be explored. It's not a finished puzzle. It's an ever-unfolding mystery. And every question you ask is a thread pulling at the fabric of the unknown. So what will you uncover next? So here is the truth, and it's both humbling and exhilarating. The deeper you look, the more the universe fights back. We've always believed that science was about uncovering the smallest secrets, the threads of reality woven tighter and tighter, until we reached the very fabric itself. But now we stand at a threshold where the rules change. This isn't just a limit of our tools or our cleverness. It's a fundamental boundary woven into the cosmos. When you push your observations to the tiniest scales, something extraordinary happens. The very act of seeing go probing collapses into darkness. You're not just hitting a wall. You're staring into the maw of a black hole, one born from the energy of your own question. Let's say you want to measure something so small that it defies imagination. You crank up the energy, sharpen the beam, refine the resolution only to find that the universe answers with a whisper. No, because at a certain point, the energy you pour in doesn't reveal more detail. It erases what you're trying to see. The space you're probing isn't just blurry, it vanishes, swallowed by its own gravitational pull. That's not a glitch. That's physics. And that scale, it's called the Planck length. A number so infinitesimal, it makes the proton look like a continent. At this size, the act of measurement itself becomes a paradox. You can't peer into the heart of an atom without bending space-time out of recognition. You can't ask, "What's smaller than this?" without the universe replying, "Nothing, not anymore." Now, let's talk about the energy it would take to reach that scale. We've built machines like the Large Hadron Collider, hurling particles at nearly the speed of light to uncover the secrets of the universe. But even that is a child's toy compared to what it would take to glimpse the Planck length. The energy required isn't in the billions of electron volts. It's in the trillions of trillions. We're talking about forces so immense that the accelerator needed to harness them wouldn't fit inside a galaxy. It would stretch for light years, dwarfing our solar system, our star, our entire cosmic neighborhood. And here's the kicker. You could build it, and it still wouldn't work, because the universe wouldn't let it. The moment you tried to focus that kind of energy into that kind of space, gravity wouldn't just interfere, it would win. A black hole wouldn't form as a side effect. It would form as the only possible outcome. So how do we know this isn't just a quirk, a fluke of the math? Because the universe has another way of telling us the same story. Let's go back to a principle you've likely heard of. Heisenberg's uncertainty principle. It says you can't know both the position and the momentum of a particle with perfect precision. The more exactly you pin down where something is, the less you can know about how it's moving and vice versa. That's not just theory. That's the way the world works. But here's what we've discovered. Gravity isn't just another force in this game. It's a player that changes the rules entirely. When you try to measure something with light, when you shine a photon to see where an electron is, the photon doesn't just bounce off. It pulls. It warps space-time in its own tiny way, tugging on the electron you're trying to observe. And that tug isn't negligible at these scales. It's fundamental. It's as if the universe is saying, you can't just ask without changing the answer. So we take this idea that every measurement disturbs what you're measuring and we add gravity to the mix. What happens? The uncertainty doesn't just balance out, it flips. At a certain point, the more you try to shrink your measurement, the more the uncertainty grows, the scales tip. The best you can do isn't to see smaller, it's to hit a floor. And that floor, it's the Planck length again. From two completely different angles and through black holes. One through the act of measurement itself, we arrive at the same inescapable conclusion. There is a smallest meaningful distance in the universe. Below that, space and time aren't just fuzzy. They stop making sense. They dissolve into something else entirely, something that requires a new kind of physics to describe. So where does that leave us? Standing at the edge of understanding, staring into the abyss and realizing the abyss is staring back. This isn't a failure. It's a revelation. It tells us that the universe isn't just a puzzle waiting to be solved. It's a living, breathing entity with its own boundaries, its own limits, its own way of saying, this far and no farther. And that should make you feel two things at once. First, awe. Because the fact that we can even ask these questions, that we can stand on the shoulders of every scientist who came before us and look this deeply into the fabric of reality, that's a miracle. Second, determination. Because every boundary we've ever hit in science was once thought to be insurmountable. And yet, we've always found a way to push further. The difference now, we're not just testing the limits of our tools, we're testing the limits of reality itself. So what's next? The answer lies in unifying the two great pillars of modern physics. Quantum mechanics and general relativity. They've ruled their own domains for over a century, and they've both passed every test we've thrown at them. But they can't coexist at the Planck scale. One describes the smallest things, the other the largest. One rules the quantum, the other the cosmic. To bridge that gap, we need a theory that treats them as equal partners. One idea is string theory, which suggests that the fundamental building blocks of the universe aren't point-like particles but tiny, vibrating strings whose size is on the order of the Planck length. And here's the beautiful part. Those strings don't just exist at that scale. They enforce it, try to probe smaller than their natural size. And what happens? The strings don't let you. They don't collapse into a black hole. They don't increase uncertainty. They vibrate differently. Their modes of oscillation change, and the resolution you thought you'd gained actually spreads. The string's size isn't a limit. It's a feature. It's the universe's way of saying, this is how small things can get. So what does all this mean for you? It means that the universe is far stranger and far more generous than we ever imagined. It's telling us that there are depths we haven't yet plumbed, mysteries we haven't yet uncovered, and that the quest to understand them isn't just about smarter tools or more precise measurements. It's about rethinking the very foundations of how we see. It's about asking not just how small can we go, but what happens when we do. And it's about realizing that every time we hit a wall, we're not just at the end of a road. We're at the beginning of something new. So let's not stand still. Let's not be daunted. Let's take this as our invitation to dream bigger, to question deeper, to push harder. Because the universe hasn't given us limits to discourage us. It's given us limits to inspire us, to remind us that every boundary we reach is just another horizon calling us to explore what lies beyond our current understanding. And who knows? Maybe one day, you'll be the one standing at that next threshold, looking out at a universe even stranger than the one we've discovered so far. So here's the revelation that doesn't just challenge your understanding of reality, but reshapes it entirely. The universe has a secret limit. Not just any limit, but one so fundamental that it defines the very edges of what we can ever know, see, or measure. Imagine standing at the threshold of a door that can't be opened further. No matter how hard you push, that's the Planck scaleth's smallest meaningful length in existence. Below it, Space isn't just unknown, it ceases to behave like space at all. The tools of physics we've relied on for centuries distance. Time, even the idea of a smooth, continuous fabric of reality all begin to unravel like threads in a fraying tapestry. This isn't a glitch in the system. It's the universe's way of saying, no farther. Now, you might wonder, how did we arrive at this stunning conclusion? Twice. From two completely different directions, and through the terrifying collapse of black holes, the other through the quiet hum of quantum uncertainty, and both paths led us to the same breathtaking truth. The first hint came from black holes, where the laws of gravity and quantum mechanics clashed in a violent dance, forcing us to admit that at the smallest scales, even time might lose its meaning. Then, through the lens of quantum measurement, we found the same boundary, hidden in the math of uncertainty itself. The universe, in its infinite wisdom, has woven these threads together. Try to probe too closely, and gravity screams back with black holes. Try to measure too precisely, and quantum fuzziness pushes back with uncertainty. It's not a flaw in our understanding, it's a feature. Nature allows us to explore, but only up to a point. Beyond that, the rules change. So where does this leave you? Not in confusion, but in a awe and in the humbling realization that you're part of a story far grander than any single equation or experiment. The Planck length isn't just a number buried in a textbook, it's a whisper from the universe itself, telling you that some questions aren't meant to be answered. At least not with the tools we have today. But that doesn't mean the journey ends here. Far from it. Theories like string theory and loop quantum gravity are stepping stones. Bold attempts to bridge the divide between the tiny and the vast. String theory suggests that the universe is made of tiny, vibrating strings, each one a universe in miniature, humming with energy at the Planck scale. Zoom out, and suddenly, Einstein's relativity emerges naturally, as if gravity was always hiding in plain sight, waiting to reveal itself. Loop quantum gravity takes it even further, painting space-time itself as a patchwork of indivisible chunks, like pixels on a screen but instead of a digital image. It's the very fabric of reality. Below the Planck scale, the smooth, continuous world gives way to a quantum foam, a seething, uncertain landscape where every measurement becomes a guess. This isn't just abstract philosophy. It's a call to action, a reminder that the greatest discoveries often come when we dare to ask the questions others ignore. The Planck scale isn't a roadblock, it's an invitation. It's telling you that the universe is deeper, stranger, and more connected than you ever imagined. And you're the one standing at the edge of that mystery, equipped with curiosity, wonder, and the unshakable belief that someday the answers will unfold. So keep asking, keep pushing, and when the universe hits its limit, remember, that's not the end. That's where the magic begins. The smallest scale isn't the end of exploration, it's the birthplace of a new understanding. And you're part of that story. Now, go find your place in it.